good at that either. I see in the hallway.
Okay, all right, here we go. We're ready to start in with some basic function vocabulary. Now, as is the case always with definitions, it isn't the exact words that are important, it's the meaning. So we want to make sure that we know what it means to be a function. So what is a function? In your own words, what is a function?
Every input has one output.
Okay, so it is we call it a relation. It's a set of ordered pairs. We're talking about inputs and outputs, so they're like two things connected. We'll call them ordered pairs. So it's some set of ordered pairs where every input, which is the x's, is paired with exactly one output. Does that sound okay? What's another way of thinking about that? Does anybody have a different working definition for a function? A set of ordered pairs where none of the x's are repeated, or none of the elements of the domain are repeated, because that's another word on our list. What's the domain?
The set of x values.
The set of first coordinates. Usually x values, and for our purposes now we can call them x values, but understand that we'll be leaving the xy coordinate system at some point and going to a new coordinate system, so it won't make any sense to call them x's at that point. It's the first coordinate. It happens to be x in the Cartesian system. That's domain. Range is the second one, the y's, that's right. Independent versus dependent variables. If you look at an ordered pair, or if you look at an equation, what is the independent, or if you look at a graph, a coordinate axis system, what is the independent variable?
X-axis.
X. It's the horizontal axis, right? Right? In function notation, which you have seen before, right? This is function notation. These are the inputs, right? You're inputting that into the function. Those are also the independent variable. So if we had an equation that looked like this, S would be the independent variable, and then f of s, this is the dependent variable. Vertical line test, what's that?
It's when you draw lines on a function to see if it intersects.
Okay, so how does that work? So let's say I have some shape. That's a classic cubic curve right there. What would the vertical line test look like with that picture?
You just draw a bunch of vertical lines.
Draw a bunch of vertical lines, and sometimes we don't even draw them. Sometimes you just lay a pencil on here or something. But what has to happen? If you are a function, you will not hit that more than once. Each individual line will not hit it more than once. Obviously, if we drew something like this, which is a nice little horizontal parabola, not an issue at all, but it's not a function because we hit twice. Think about it. This might be the point -2, 5, and this would be the point -2, -2. See what happens? If you're on the same vertical line, you have the same x coordinate, and that doesn't fit your definition. That's why you're not a function. All right, a mapping. I don't know. Last year, did you guys ever describe your functions with what we call a mapping? It looked like this. So let's say this is my function, and my domain is 1, 2, 3. If I plug 1 in, I get 7. So a mapping would just look like this. 2 gives me 10, and 3 gives me 13. That's called a mapping. All a mapping is, it's not a big deal. It's simply a different way of expressing your ordered pairs. This is the ordered pair 1, 7, and so on. Now, if you have a mapping, okay, so it's not this anymore now. If you have a mapping that looks something like this, now that still describes ordered pairs, but it does not describe a function because this would be used twice. All right, let me take that pink one out. Let's put this purple one in. Oh wait, that's not what I meant to do. Is that a function?
Yes.
It is, because none of my x's have been used twice, but my y's have, but it doesn't matter, no one cares about the range, right? Just the domain is the important one. All right, continuity. Mr. Miller said you guys hadn't talked about this before, but you heard what he said. Basically, if you can draw your picture without lifting your pencil, it's continuous. Now, he and I kind of speak the same language, we kind of roll on the same plane. That is not like what a calculus teacher is going to say. A real life calculus teacher is going to give you the definition of continuity, which is I've written it out there for you. Isn't it lovely? That is just the way of saying, if you can draw your picture without lifting your pencil, you are continuous. Let's look at the different kinds of continuity. The first graph there is continuous. Clearly, if I try to draw it, I don't have to lift my pencil, so I'm all good. Look at the second one now. This is called a removable discontinuity. And Mr. Miller and I, in our math vocabulary, will say that has a hole in it. That picture has a hole in it. Any picture that has a hole in it, that hole is called a removable discontinuity. Now, there are a couple of ways to have a removable discontinuity. You can have it the first graph or the second graph that says removable discontinuity. What's the difference between those two pictures? The second one and the third one, the ones that have removable discontinuities, what's the difference?
One has the dots.
One actually has a value at A. It has a point plotted at A, but it's above the rest of the curve. The other one has no value at all for point A, value of A. There's no point at all. So those are the two ways you can have a removable discontinuity. You can have a hole in your picture, wherever that hole is, you can have a hole in your picture, either with nothing at all, or with a value somewhere else in that line. This would still be a function, correct?
No.
Whoa, 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 whoa. That's an empty dot. That's not included. So when I draw a vertical line down through there, how many places do I actually hit the curve? Once, right there.
What about the dot there?
It's like a number line, Marin. Does that include 3? Does that include 3?
Oh, no, okay.
No. All right, then we have what's called a jump discontinuity. A jump discontinuity is exactly what it says. The curve goes along for a while, and then all of a sudden it takes a jump and starts in again. And then they can do that again. They can do that as many times as they want. But that's called a jump discontinuity. Clearly, everything except the first one is discontinuous because no matter which one you're looking at, you have to lift your pencil. And finally, the most major discontinuity, the most powerful one, is the asymptote. So they call it an infinite discontinuity. It is a non-removable discontinuity. There is no way to fix the problem. If you have an asymptote, you cannot fix that problem. An infinite discontinuity is like the strongest of all discontinuities. It completely breaks your picture into 2 chunks, or 3 or 4, however many, and there's no way around it. We're running through vocabulary. In a minute, it's going to take us a while, might be next class, we're going to look at specific functions and then talk about each of these words, okay? Right now, we're just kind of looking at the words and figuring out what they all mean. Increasing, decreasing, pretty easy to understand. Again, Mr. Miller and I are going to talk about it like this. As I draw my curve from left to right, if my pencil goes up, I am increasing. If my pencil goes down, I am decreasing. It is clearly possible for one picture to have both going on. It can also have no increase or decrease if it is horizontal, right? Horizontal. Okay, so look at the pictures. Do you get the first one's increasing, the second one's decreasing, the third one's constant, not doing either. And then that fourth one, do you see what they're talking about? We are decreasing until we get to -2. And then we are constant from -2 to 2. And then we are increasing from 2 on. I'm not going to argue about it. I'm not an expert by any means on it. But the way your textbook does that, that's where I got this, bothers me. I would say it is decreasing from -infinity to -2. And I would use a parentheses there. And then I would say it's constant from -2 to 2, yeah. And then I would say personally it's increasing from 2 to infinity. Now, I am never gonna mark it wrong, kids. I'm not gonna argue with you. I have to think I'm right. I'm sure this guy thinks he's right. It bothers me that a single point can be increasing, decreasing, and neither at the same time. Do you see what I'm saying? And that's how he has listed it. Anyway, for what it's worth, I don't care. It's fine this way, it's fine the way they did it. You will be expected to define intervals on which we are increasing or decreasing. Boundedness. Again, you've got your formal definition there. You're gonna read these on your own. No one, at least not this year, is going to ask you to write these definitions. You have to be able to use these words and to identify boundedness, for example, in a given situation. Here's what boundedness means to me. Do you have a ceiling? Is there a ceiling on your picture, your graph? Is there a point beyond which the curve can't go? So here's an example. If I have a picture that looks like this, there is no upper bound, because you see what this is doing? Forever, no upper bound here. But if I have a picture like this, there is an upper bound, because no points of the curve are higher than that one, so that's considered an upper bound. Now, would this curve have a lower bound? No, because these guys are shooting down forever. There's no floor. Does that one have a lower bound? No. This one is considered totally unbounded. It's forever up, forever down. This one is considered bounded above because it has an upper bound but no lower bound. Did you have a question, Leah?
So will a parabola always be bounded below or bounded above?
Yep, absolutely. So will an absolute value. Remember your absolute values are these? So they're always going to be bounded above. When we look at our sine curves, which we're going to do in the next few days, sine curve looks like this. It is bounded above and bounded below, so it's considered to be bounded. When you say something is bounded, you just that word, bounded, that means it's above and below. Otherwise, you say bounded above or bounded below, depending on your picture. Oliver?
On that sine curve, would you be asked to find where it's bound below and above?
You would. Now, that we're at this point in our life, we're only going to look at the basic sine curve. So it is between 1 and -1. Those are the basics. Certainly, you can use your calculator if you have some modification of that or some other picture. You can use your calculator to find the maximum and the minimum. That would be where the bounds are. But for a basic sine curve, which is the only one we're going to look at, we're going to look at what's called your BFFs, basic family of functions, and the sine is one of those. I gave you a handout of those, and we're going to be looking at that soon. And we're going to look at those curves and answer all of these questions. All right, extrema. Gotta hurry up, or I'm not going to get through my vocab. The extrema. What we mean by extrema are high points and low points. So I think of it as tops of hills and bottoms of valleys. So, Leah's question involving the parabola. A parabola opening down will always be bounded above, right? And that point right there, that vertex point, will be its maximum. Extrema are maximums or minimums. There is another kind we'll talk about another time, but for now, maximums and minimums. Now, there are two kinds of maximums that you can have. Look at the picture that I drew there. Would you agree that B and D are both maximums? Okay? B is a little bit higher than D, but they are both considered maximums because they are the high point in that little part of the graph in which they're located. They are called relative maximums because they are maximum relative to the points on either side. This problem has no absolute maximum because why? Why is there no absolute maximum?
They go up forever.
Because it's shooting up, right? Now, if we had a picture that looked like this, this and this would both be relative maximums, agreed? But this one would also be the absolute maximum because it is the highest point on the picture. So being a relative maximum means in your little area of the graph, you are the highest point, the hill right there, you're the highest point. Same thing here. If you are the highest relative maximum, then you're the absolute maximum. And the same thing is true of minimums. Okay, so what are you going to say about point A on this little picture I drew there?
Absolute.
Absolute min. What are you going to say about E? Relative min. What are you going to say about C? Relative min. And then B and D are both relative maximums, and there is no absolute maximum because of the arrows. Okay? Now, we're going to talk about symmetry. What does symmetry mean to you? Just when you hear that word, what do you think of? It's the same on both sides. So I'm going to go back to my little parabola there, and I'll turn it right side up. Do you remember this from last year? That's what that little parabola looks like. That's one of our BFFs. You'll get very, very familiar with it. Does that have symmetry?
Yes.
About what? It's symmetric about what? The y-axis. A curve that has symmetry about the y-axis is called an even function. So if someone says to you, you have an even function, it means it has symmetry about the y-axis. When I give you a picture, it's easy. The test, the formal test for even functions, for symmetry to the y-axis is, take your equation, here's my original equation, now change the sign on x. In other words, take this point right here and see what happens to its sister point, negative x. If this is exactly the same equation as this, which it is, right? Then you have symmetry. That's your test for symmetry about the y-axis. So let me give you an example of one that's not. And there are lots of them. let's say we have the equation 3x plus 2. If I change the sign on x and simplify, do I get the same equation as I started with? No. So that one does not have symmetry about the y-axis. The test for evenness in function land is change the sign on x. If you end up with the same answer, then you are even. Your function is even. All right. Let's talk about symmetry about the x-axis. Now I want you to think about that for a second. Would this picture have symmetry about the x-axis?
Yes.
Because if I put in, let's say this is the point right here, the point 2, 3, what would this point be? So in other words, changing the sign on y should yield the same x values, right? So let's see what that test looks like. Let's test this one for symmetry about the x-axis. There's no special name for that, by the way. Evenness goes with the y-axis. There's no special name that I know of for the x-axis. Change the sign on y. Is that the same equation that I started with if I change the sign on y? No. But what if I did this? What if I had the equation x equals y squared plus 4? And I said to you, does that have symmetry about the x-axis? Well, you'll change the sign on y. Does that give us the exact same equation? So yes, this equation has symmetry about the x-axis. All right, remind me next time that we need to finish up the symmetry, and then we'll be ready to go.
This board.
Yeah.